So now you're feeling pretty good about power rule, chain product, quotient rule, and you can take the derivatives of most functions, and then you encounter something like this, x to the cosine x power. How do I do this? We need a new technique called logarithmic differentiation. Let's get started. The idea behind logarithmic differentiation is that we're going to use the properties of logarithms to simplify a function before we actually take the derivative. And then we're going to use implicit differentiation to figure out our final answer. So first we need to review a few principles of logarithms. Now for our purposes, we're just going to look at the natural log, which is log base e. I call it ln. Now these principles apply to all logarithms, and if you need more review on that, I have another video going over principles of logarithms. You can find the link to that video in the description of this one. But for now, let's just look at the principles we have here. So if I have the natural log of two things multiplied together, like natural log of ab, then I can break that up as natural log a plus natural log of b. The idea is you got to think about these natural logs as an exponent. So what I mean by that is if I had, for example, y equals e to the x, and I want to know what power of e is x, that's where the natural log comes into play. So if I have e cubed, for example, and I take the natural log of e cubed, that's just going to spit out my exponent. And exponent is the key word here. Logarithms spit out the exponents of what's plugged inside. So for example, if I have two things multiplied together, what do I do to their exponents? I add them. That's why ln of ab equals ln a plus ln b. Similarly, ln of a divided by b turns into subtraction, because what do I do with the exponents when I divide two things? I subtract their exponents. And the third one is going to be a very powerful one for us, and that is if I take the natural log of a to some power, a to the n power here, I can take out that exponent and turn it into multiplication. So for example, if I revisit this first equation, y equals e to the x, if I take the natural log of both sides, then I'm allowed to, since the x is the exponent of e, I'm allowed to bring that out front and turn it in multiplication. The reason this is really nice for us is because a lot of our algebra breaks down if we have a variable in the exponent. Natural logs find us a shortcut or a loophole to get that exponent out front to now turn it into the normal algebra that we're used to. A few key facts to know. Remember, these are exponents that pop out. So when I say ln of 1, I'm thinking e to what power is 1? E to the 0 power is 1. So ln of 1 is 0. Ln of e, well, e is e to the first power, so ln of e just becomes 1. And ln e to the x just reduces down to x. And you can see that again in this equation. I have ln y equals ln e to the x. That turns into x ln e. And then ln e is 1. So we just get y, which is exactly what I was saying at the beginning. Another way you can think about this is natural log and e are inverse functions of each other. So when you compose them, they cancel each other out. You just reduce down to x. Alright, so how do we use this to take derivatives? That's what we're really here for. All this is just algebra. Alright, let me show you. So here I want to find y prime, or y equals x to the cosine x power. Do not try power rule here. That will not work. That is incorrect. You can't do that. But what I can do is take this equation and take the logarithm of both sides. Sometimes when I have students and they're trying to take the natural log of something, they want to apply power rule, but that doesn't work because ln is not a number, or it's not something being multiplied by x cosine x here. X cosine x is inside the logarithm function, so we're going to have to use chain rule if we take the derivative of that directly. Before I take the derivative now to find y prime, we should use our properties of logarithms to bring that cosine x out front. And so now I have cosine x times ln x. See, that's very clever. Now the difficulty of the question is basically removed, and that's ln y. So now when I take the derivatives of both sides of this equation, the derivative of the natural log of x is 1 over x. So when I take the derivative of ln y, I get 1 over y times the derivative of y, which is, this is a chain rule being applied. So we'll call that y prime, and this is implicit differentiation. On the other side of the equation, I do have a product rule situation now, but that's only because I have cosine times a natural log. So to apply power rule, I say the first times the derivative of the second. The derivative of natural log of x is 1 over x, plus ln x times the derivative of the first, which is negative sine x. So now what I can do is multiply both sides of my equation by y, and I solve for y prime. So I have y prime equals y times I'm going to write this as cosine x over x minus sine x natural log x. And there's my derivative. The only thing I need to do is replace y with the expression of x, but remember at the beginning, y is x to the cosine x power. And so there's my derivative. I hope that makes sense. Let's try another one. Similar thing here, we have y prime. We want to find y prime, y equals x plus square root of x to the 1 minus x squared power. So my old derivative laws don't work here, so I'm going to have to apply the natural log to both sides of my equation. And again, the reason that's useful is because now I can take that exponent and bring it out front. So I have 1 minus x squared times the natural log of x plus the square root of x. Okay, now I want to take the derivative of both sides. Be careful here because we are going to have to do some product rule and some chain rule. We have 1 over y times y prime. And then now I'm going to apply product rule. So I have two derivatives here. I have two functions being multiplied together. So I have the first, 1 minus x squared, times the derivative of the second, which I'm going to just write like this for the moment, plus the second, which is this ln x plus square root of x, times the derivative of the first. So I kind of wrote it like that so I can break down my derivatives one at a time here, and I actually made a mistake. The d2 is actually the derivative of ln of x plus square root of x. So now applying those derivatives, I have 1 minus x squared. The derivative of ln of something is 1 over that something times its derivative, right? 1 over u times du dx. So that's going to be 1 over x plus square root of x times the derivative of x plus square root of x, which is going to be 1 plus, and don't forget, square root of x is x to the 1/2 power. So that's going to be 1/2 x to the negative 1/2. That's just power rule. On the other side, I have ln of x plus square root of x times the derivative of 1 minus x squared, which is negative 2x. The last thing I need to do then, this is 1 over y prime, is the derivative that I want is just y times all of this stuff, which is very ugly, and that's okay. I'm going to say 1 minus x squared over x plus square root of x times 1 plus 1/2 x to the negative 1/2 power, and then you have all that plus, or actually minus, 2x ln x plus square root of x. And so I just need to rewrite all that, and instead of writing y, I write what y equals, which is this x plus root x to the 1 minus x squared power, times all this stuff again. Okay, now I didn't say it was pretty, I said it was doable, and it's actually not very difficult. We follow these same steps over and over. What may have made this question difficult is that I had to apply chain rule here in an awkward way. We also had to apply product rule at the beginning when I take the derivative of both sides. And another thing I see that students forget a lot is they'll just leave their answer like this, y times this big thing. We actually need to replace y as an expression of x, which is this x plus square root of x to the 1 minus x squared power. Make sure you include that. Other than that, we kind of just rinse, wash, and repeat. If you have questions, let me know. Let's look at another one though. Okay, so this time I don't have like x to some power or variable exponent. I have something I could just handle with product rule, quotient rule, chain rule, things we know in the past. But I want to point out that logarithms actually can make this easier on us. If I have y equals x squared times the square root of x plus 2 over tan x, and I apply the natural log to both sides of this equation, the properties of logarithms we had at the beginning said that if I have the ln of two things multiplied together, like ln AB, that's ln A plus ln B. So I do have multiplication here. I also have division. And we said division can turn into subtraction. So here I could rewrite this as ln x squared plus ln. For the moment, let me write x plus 2 to the 1/2 power, and then minus ln tangent x. Okay, what's nice about this now is to also remember I had the exponents can be pulled out front as multiplication, which we've used that fact several times now. So this is 2 ln x plus 1/2 ln x plus 2. That's why I wanted to write the square root as a 1/2 power. And then ln tangent x. And this equals ln y. So now if I take the derivative of both sides, just like we've done in the past, these three derivatives are way easier than the derivative that we started with, or the function that we would have to take the derivative of at the beginning. So I take the derivative, I get 1 over y prime equals the derivative of ln is just 1 over x. So I have 2 over x plus 1/2 times 1 over x plus 2. And then tangent, okay, I'm going to use chain rule here. It's 1 over tangent times the derivative of tangent, which is secant squared x. So now y prime equals y times all of this. And I'm going to write this as 2 times x plus 2 in the denominator, minus secant squared x over tangent x, which we could definitely simplify if we wanted to. I'll just leave it like that though. And now all I have to do is replace y with what I started with, the x squared times x squared times square root of x plus 2 over tangent x times all of this. Alright, so there's my derivative. Actually, we can use properties of logarithms to deduce some of the formulas we know. We use product rule here. So how about we use logarithmic differentiation to develop product rule? What the product rule is about is trying to find the derivative of two functions being multiplied together. So I'm going to have f times g, and I'm going to call that y. And so I want to take the derivative of f times g. And the way I'm going to do that is, instead of using product rule, I'm going to take the natural log of both sides of my equation here, which we know that product of inside a logarithm turns into the addition of those two logarithms. So I have ln f plus ln g. Now when I apply implicit differentiation, I have 1 over y prime equals the derivative of ln f is going to be 1 over f times the derivative of f, which I'll write as f prime, that's just chain rule, plus the derivative of ln g is 1 over g times g prime. Okay, so now all I have to do is multiply everything by y, and so I have f prime over f plus g prime over g times y. And remember, y was f times g. So now when I distribute the f times g across, look what happens. I have f g f prime over f, and here the f's cancel. And I have f g g prime over g, here the g's cancel. And I'm left with g times f prime plus f times g prime, or the second times the derivative of the first plus the first times the derivative of the second. This is product rule. Alright, so in a way we proved product rule using logarithmic differentiation. I hope that you can see logarithmic differentiation is an extremely valuable tool. It helps round out our derivative toolbox. If you need help with this, let me know. I'd be glad to help. I hope you learned something, and thanks for watching.